So there's general relativity, which was published in 1916, and it is supposedly a model of gravity, as indicated by these red lines here, but it does not have a model of matter. Okay, then we have quantum mechanics, which began in the 1920s, which is a model of matter, but it doesn't have a model for gravity. So one would think that they should be able to marry these two things together to come out with a coherent model of matter and gravity and give us a unified field theory or a theory of everything. Well, folks, we've been waiting for 100 years and nothing has happened on this point. In this video, I'm going to show you how broken science is, and then I'm going to propose a replacement to the scientific theory, which includes rules for determining how good theoretical models are. Okay, to see the disarray, just go and Google black holes. Okay, here you got Brian Cox, how black holes could unlock the mysteries of our universe. Which we don't already know? I mean, if I would think a coherent theory of everything would be better, would tell us everything. And how are you going to know unless you actually go to a black hole? We're only seeing black holes from incredible miles away with the instruments we have. How, unless you're up close and be able to detect the properties of a black hole up close, how can you be sure? Okay, and then why black hole environments are a lot more complicated than we thought. See, we don't even know. We're changing our mind. We're wrong. It's more admission that our 100-year-old models of space and time are not correct. And why do they waste our time with this? Okay, here, what's inside a black hole where reality breaks? I'm sorry, if we have a theory of everything, then our model of our theory of everything will tell us what's going on inside of a black hole, and then that's the reality for a black hole. If we say it's where reality breaks, it means we don't really know. We're just making this stuff up as we go along. Okay, then you have this guy that says black holes are portals to other dimensions, and you can see the question mark in there, which means that this is really just conjecture. These scientists are making up stories to sell books and to sell clicks, because in the next story he's saying, is our universe inside a black hole? Again, with the question mark. Seriously, we don't know. Okay, in essence, until a theory of everything is developed, anything you hear from these people is just fanciful speculation designed to sell their latest books. It's not good enough to even be called science fiction, because at least there you have a plot. And this is one of the many reasons why there's no progress on a theory of everything, is because there's no real consensus in science. And really, until we can actually get to these places, we can't really even be sure of the theory. All of our observations of the universe are from the tiny scum layer of the Earth. And the odds that we're going to be using our telescopes and looking to the distant extremes of the universe and be able to get anything right is problematic at best. And therefore, we can assume we're not working with complete models. That's going to be another thing I'm going to show you, the reason why they can't unify quantum mechanics and relativity. So what I'm going to be getting at is I'm going to show you that science is broken. It's actually rotten to the foundation. I know some of you are saying, and this is what's coming into your brains right now, is say, well, if something were wrong, somebody would have said something by now. I'm going to show you this is one of the most damaging myths in science. The other thing that might be coming through your brain right now is, well, how could we have all this high technology if science were broken? We're going to start with this question first. Okay, and basically, this is covered by the third rule of acquisition, which we're going to get into, but there'll be a full video on this later. It's called Monkey Do. Just because we can put stuff to high technology does not mean we actually understand what it is we're doing. And I'm going to show you proof evidence of the case in a lot of branches of technology. Okay, and let me give you a case in point right here. Humans used fire for over 100,000 years to heat their homes, burn down the homes and crops of their enemies, even up to the early development of steam propulsion, steam locomotives, steamships. Humans still did not know what fire was. And I'm going to show you at the end, we're still not really sure what fire is completely, but we'll discuss that at the end. But this goes to show you that not knowing what something was did not prevent us from observing and measuring what it did in order to develop technological applications, otherwise known as empirical models. So the empirical method is very simple. You observe nature, you develop a model which is nothing more than a means to mimic. Okay, and then you develop technological applications around that model, and then that improves technology, which then improves the empirical method. And the origin of the word, empirics, were members of a sect of doctors who practiced medicine using treatments observed to be clinically effective. Notice, what did it do, rather than a treatment based on theoretical principles. In other words, we do this because we know that it'll work. We don't really care what the underlying reason or mechanism is. So essentially, empirical methods are nothing more than monkey see, monkey do. Now, I'm not trying to be denigrating to science. What I'm trying to do is put things in terms that the average guy will understand, because a lot of the definitions of science are so construed with words that mean only different things to science than it does to the regular dictionary, that it's sometimes very hard. And I'll show you examples of this. Okay, again, empirical models, empirical method. The important point is that the people that are doing this, we call them empiricists, are only concerned with what something does. They don't care what it is, they don't care what makes it work, and they don't care about any underlying mechanisms or theory. Now, what we're going to do for this new definition of science, we're going to separate the empirical side of technological development from the scientific side of scientific development, and this will be part of the scientific side. And I'm going to show you we can do a lot with empirical methods, which means we don't really know what we're doing. We just know, monkey see, monkey do. We repeat, we make it work. It doesn't mean we know exactly what it is that we're using. For many, many years, people thought fire was an element or that it was a living thing because it grew and spread. So there was a lot of myths about what fire was, and that did not stop us from putting it to good use. Okay, and we can go back, look at gunpowder. Gunpowder was invented probably by trial and error in China. It made its way to Roger Bacon, who recorded its recipe. And I thought Roger Bacon was the guy that improved the formula, but that's not really written anywhere. But anyway, somewhere along the way, the recipe was optimized ostensibly by trial and error, just mixing together different combinations of the materials until you got the biggest bang possible. So essentially, this was the original Big Bang theory. The practical light bulb, Edison tried 6,000 different filaments before he came upon tungsten as the ideal material for filaments. Again, technological improvement, you see I'm separating it from scientific. So technological improvement occurs without needing any chemistry or science, other than just let's try a whole bunch of different things and see which one works best. Okay, triode vacuum tube. A tinkerer by the name of Litaforce added a third filament to a electron tube and revolutionized electronics. Now, this was developed somewhere around 1905, and this is the history of the electron, and that occurred somewhere before not knowing what the basic unit of electric charge was, and finally doing the oil drop experiment and nailing it. So somewhere in between here. So he didn't have to know what an electron was or what its weight was or anything about or the basic charge of an electron for him to make improvements to technology. In fact, up until this point, Maxwell's equations were treated as if charge were a continuous fluid. And using that model, which is wrong, engineers developed a whole bunch of interesting, fascinating things. Not knowing that what an electron was did not stop the advancement of technology. Penicillin. On 3 September 1928, an accidental contamination of a bacteria culture led to the discovery of penicillin. Completely accident discovery. Luckily, Alexander Fleming saw that the bacteria wasn't growing on the contaminated plate and realized that was a good thing. But here's more important, even after he developed that, the mass production of penicillin, they did a massive worldwide search to find different strains of the mold and finally found a rotten cantaloupe in a Peoria, Illinois market, and this ended up producing penicillin at 6 times the rate that Alexander Fleming's mold did. Again, brute force trial and error methods, even the method of mass producing it and fermenting it or whatever the name is, that was all done by trial and error. They did not have any kind of model that said, you do it this way. They just did trial and error and saw what worked the best. Again, We're not using science, we're using empirical methods to improve science. Okay, so ultimately, technological progress is the higher goal, because technology is our capabilities. It's our ability to measure. It's our ability to mimic things. It's our ability to compute. It's all of our scientific and technical capabilities. Okay, and empiricism can be used to improve technology, as well as what we're going to call scientism or science. In this case here, we use empirical methods, hands-on. We measure things and do trial and error until we can improve the technological capabilities. In this case here, we try to look deeper at the underlying patterns and maybe even come up with abstract models to replace real underlying mechanisms until we can actually determine what the real underlying mechanisms are. And we can use scientism to advance technological prowess as well. And I'm going to show you in a later slide that we humans start off with empiricism and then we switch to scientism. And this is when technology really takes off, because we have found the underlying structure of nature, we now have a treasure map which just allows us to find things fast. We'll give an example of that. So what we're going to do here is we're going to expand the definition of empirical methods. Not only does it include empirical models, but it includes trial and error, tinkering, accidental, all the ways that things were discovered before the advent of science, where we're looking for underlying causes and effects, underlying models. Okay, this is how the wheel was discovered. This is how everything up until probably the 1700s, everything was developed before then. Okay, so what is this video series? This is the introduction to Distinti's rules of scientific acquisition, which also includes a improved scientific method, which is now separated from technology. And the objective of the new empirical method, the new scientific method, is to advance technology. And we're going to show you how that feeds back to improve everything else. Okay, along with this, one of the more important parts are the rules of acquisition, which contains 18 tells that show us where our models are deficient and why they will never be part of a theory of everything, because I have determined 18 tells, so you don't have to wait for falsification. And that is one of the primary drawbacks of classical scientific method, is you cannot have progress until you have falsification. Okay, and so that by doing this, we can short circuit hundreds to thousands of years of stagnation from technological development. And this is the new technological progress curve. In the early days of any technology, this curve can be applied to any technology. In the early days, we used mostly empirical methods, okay, because we don't have enough to form an underlying pattern to look for. And this may go on for hundreds of thousands to tens of thousands of years until we hit the Mendeleev point. And we're going to show you an example where Dmitri Mendeleev saw the underlying pattern of chemical elements and was able to form the periodic table of the elements. And by doing that, we supercharged science. Now that we had a treasure map, in this section here, we end up using both scientific models and empirical models and refining the scientific models. At this point here, we're using mostly scientific models. And then we get to this point here, all the significant models are found. This is the Scotty point, where engineers take over and they develop the technology to wherever it's going to go. And scientists basically go off and find something else to do. That's the Scotty point. Okay, so in this introduction video, I'm going to show you that the present scientific method is ambiguously defined and it does not reflect the true nature of technological development. In fact, it has a drawback of having to wait for fallacies before you can have progress, which is the cause of stagnation. And we'll also show you that fallacies and superstitions stagnate scientific development. And then we're going to introduce some of the tells to help identify faulty or incomplete models and theories. So let's show the confusion of the old scientific method. So this is a model from Amy Cowan of Science Buddies. Here they start off with asking a question, which is really confusing. Nothing starts by a question. You have to make an observation and go, hey, why is that true? Before you can ask a question about it. So it's kind of not really how things work. In fact, they construct a hypothesis and they do an observation down here again. So this is a little bit more, other than the hypothesis part of it. This is a little like a mixture together of empirical and scientific methods. And I'm going to show you we need to separate the two to optimize them. Okay, because really asking a question first is not really the best way to start a scientific method, because everyone knows that Isaac Asimov didn't ask a question until he had an observation, essentially getting hit in the head with an apple. Okay, and so let's look at the Wikipedia definition of the scientific method. Again, the scientific method is an empirical, again, we're going to separate this, for acquiring knowledge that's been referred to while doing science since at least the 17th century. Okay, I'm telling you right now, we've been using empirical methods since the days of the Roman engineers, where they tried different formulas for Roman concrete till they found the one that worked the best. Okay, arches and architecture and the large Roman structures were done using empirical methods and the early versions of mathematics. Part of the problem I have with this Wikipedia is that if you go down here, it says the scientific method involves careful observation coupled to rigorous skepticism because cognitive assumptions can distort interpretations of observation. Now, if you're a person that has no idea what the scientific method is, let's say you're a student, a grammar school student, middle school student, whatever, and you come and read this because you want to learn what the scientific method is, you're going to be totally lost of what's going on here. And part of the reason why you just can't go look up these definitions here, because they don't mean the same thing to the regular definition of the word as they do to the scientific definition of the word. So a lot of this is really just total confusion. And I mean, look at this, because cognitive assumptions can distort interpretation of the observation. For example, your prior knowledge affects what you believe, and that's one of the rules of acquisition. In other words, before the 1900s, science believed that the only thing that made light and heat was fire. And so before the advent of nuclear power, they believed the sun was a burning ball of anthracite coal. You see, what you already know can affect how you interpret what you see. And the rules of acquisition cover a lot of these traps and fallacies to hopefully prevent from doing this, because had we had these rules of acquisition, they would have known right off the bat that some of these things can't be true because they violate a rule of acquisition. Okay, but the bigger problem of this old scientific method, the part that can cause loss of life and damage, is this part here, is that there's no theory can ever be considered final. Okay, again, another word that means something different in science than it does, since new problematic evidence might be discovered. If such evidence is found, a new theory or may be proposed, or more commonly found that modifications to previous theories are sufficient. In other words, you cannot have scientific progress unless you find a falsification, a point where your old theory doesn't work. And this is one of the major stagnations of science. And there's another thing in there that we're going to show in the next video when we cover the rule of acquisition 39, the uniqueness fallacy, where I've had somebody tell me when I developed a new model of induction that they said Maxwell's equations are irrefutable. Well, forgetting the fact that Maxwell's equations are not irrefutable, just because you haven't found refuting evidence to a theory does not mean it's the only theory that exists. And that's another one of these falsifications, one of these lies that are taught from one generation of science to the next. And we're going to show you that in the rules of acquisition, especially when we get to the next video where we're going to cover the uniqueness fallacy. And because of this, I'm going to show you an example where hundreds or thousands of years may occur before the counterexamples, the falsifications, are found. And this delay in technological advancement will likely lead to suffering, possibly even the extinction of the human race. Because consider this, the entire human race is on one planet. So we have all of our eggs in one basket. We are one supervolcano, one mega asteroid impact, one major plague, one worldwide nuclear war away from extinction, or at the very least, being blown back to the Stone Age. If we want to save the human race, and I will argue the ecosystem of the Earth, we need to move people off this planet in numbers in the hundreds of thousands, if not billions of people, to greener pastures, which means we have a lot of science to go. And we need not to be waiting 100 years for them to unify gravity model with a model of matter. Okay, we need to short circuit that stuff now, and I'm going to show you examples of how we could have short circuited thousands of years out of old theories. First, though, we need to get into some definitions. Okay, so technology, the word I'm defining is human capabilities, which include, but are not limited to, the ability to measure how precisely we can measure, how accurately we can measure, how frequently we can measure, how densely we can measure. The ability to compute and lots of data, to record data, to observe data, the ability for us to move, how fast we can go, how far we can go, how deep we can go, how deeply into space we can go. The ability to manipulate stuff like matter, energy, and fields. The ability to compute, oh, that's already in there. And the ability to archive and transfer knowledge. There's a lot of other things that we can put in there. It's basically our capabilities. Now, it's interesting because you see the ability to record, observe, and compute. Okay, notice that that is part of the empirical method. And so as we improve our technology, we also improve our empirical and scientific capabilities. So this is the relationship. We use empiricism and scientism to improve the technological footprint that we have. And this, in turn, leads to the improvement of the empirical and scientific methods. Okay, that is the important relationship, and this is how it snowballs and gets faster and faster and faster. Okay, our footprint. This is the human extent in the our extent in the universe, the extent of our technology, the extent of our knowledge, the extent of how we live in the universe. Right now, we're limited to the scum layer of the Earth. And our extent in time. In other words, how long have we been existing in the universe? And I would argue that's how long that we've been actually taking precise measurements of the universe. That's the more important part there. Okay, and again, it's when our footprint expands, when our capabilities expand, or our extent in the universe expands, that's usually where we find the falsifications that in the old scientific method would lead to progress. And unfortunately, it may take thousands of years for the footprint to expand at the right location at the right time to find counterexamples. And therefore, we cannot rely on the expansion of the footprint alone to have the progress of technology. Okay, the other definition is what I'm going to call mechanisms of nature. Everything in nature is comprised of underlying mechanisms. That once we understand the underlying mechanisms, now we know what's going on underneath the rest of the puzzle, if we get it right. And so the idea of the empiricists work on the surface to gather as much information as possible. And then from that, the scientists can piece together and try to infer what the underlying mechanism is. And that's how empiricists and scientists work together. Now, it doesn't mean they're separate people. In most cases, in the early part of any technology, everybody's an empiricist, and one or two empiricists, may one day see the puzzle, and they're starting to do science now. So they can be the same people. And rule of acquisition 10 is the observable knowledge trap. Models up here may be incomplete, like relativity is incomplete because relativity needs dark matter in order to get a complete answer. But unfortunately, it's ironic that relativity doesn't have a model of matter, so how could they be all of a sudden theorizing about dark matter when relativity does not have a model of matter? So anyway, so your models at this level may be incomplete or in some cases wrong, and we're going to show you where Mendeleev had that problem. So trying to infer from here, trying to derive your models at the upper level, at the empirical level, down to the scientific level, is problematic, and it's probably not going to work because you cannot go from here to here if you are missing pieces or you have incorrect pieces. Okay, and let me show you an example of that, why it's difficult. Because here you have salt. Salt is necessary for life, and it's a crystal. It is composed, at the lower level, it is composed of chlorine gas, which is toxic, and it's yellow, but you don't see really any yellow here. It's also comprised of a metal called sodium. Metal is also toxic to life, but you don't see any metallic properties here. So trying to infer the underlying mechanism from what you observe at this level is problematic at best. Okay, and that's rule of acquisition 10. That is the higher knowledge trap. You got to be careful. So the idea for this new scientific method is you have to infer down and then see if what you combine together produces what you're seeing at the upper level. And we're going to show you how Mendeleev did that, looking for the elements. So the new scientific method, I'm calling it new because really what I'm doing is separating the empirical part from the science part, requires scientists to theorize about the underlying mechanism of nature by looking for patterns in the existing footprint, which includes all the existing empirical models, other scientific observations, or to expand the footprint to acquire new evidence. Okay, so in other words, once they theorize, then they mimic that theory with a mathematical model, and then what they do is then they derive that model from the lower level up to the upper level and see if the model predicts the observable inputs. And then what they do is they explore the model to find other phenomenon that can be measured that may be presently unknown. That's what Mendeleev did. We're going to show you that example in a little bit. Okay, but again, technological progress is a higher goal. Empirical models are based on observation and only care what it does. And the scientific models are based on a theory, and they ask, what is it? What makes it work? Is there an underlying pattern or mechanism? They also care about what does it do. Okay, the empirical method, you can read this for yourself. I'm not going to go over it again. These are just the formal definitions. Empiricists are people that use the techniques. Scientists use the scientific method we just discussed. And again, by studying the empirical and looking for underlying natural mechanism, it's possible that two seemingly different phenomena are from the same underlying mechanism. That's how electricity and magnetism was pulled together. In other cases, knowledge of the underlying mechanism enables them to predict the existence of other phenomena that may not yet have been observed. And here is the example. Okay, in 1806, John Dalton had his table of known elements right here, and I love the old alchemy symbols. That's pretty cool. And they had measurements for the weights or the densities of these materials. And all of this was acquired by what we're calling now empirical or trial and error methods, whatever you want to call it. They did not have a scientific roadmap of what all the elements were or where they could be found. And so we're just bouncing around, empirically finding stuff. And as we find stuff, we catalog it. Then this guy came along, Dmitry Ivanovich Mendeleev. By identifying the underlying pattern of the elements, he correctly predicted the properties. He corrected properties of known elements that were incorrectly measured, and he predicted the existence of unknown elements that were later discovered. Essentially, now that we have a treasure map, finding the treasure is done with less guesswork at a much faster rate. So again, by finding the underlying treasure map, we can cut out a lot of stagnation. And this is his early periodic table of the elements. You can see it kind of looks like solitaire because that's what he would do on the train every night home from work, is he had a deck of cards with the elements and he would lay them out in different ways to see, is there a pattern there? And that's why kind of the periodic table of elements looks like a solitaire game. Okay, and let's show how technology progressed in this particular point here. So for a long time, people were finding elements by trial and error, doing empirical methods, by finding them by accident, yada, yada, yada. They made a lot of mistakes in some of the measurements. And then along comes Mendeleev. At this point, he found the underlying pattern. So now we're beginning to transition from empiricism to scientism, going from empirical models to scientific models that have an underlying mechanism that allows us to identify things quicker. And because he had the roadmap, he was eventually able to use other methods to improve it and improve it and improve it and improve it till he had a very good model, and they found a lot of elements really, really fast. Then we get to the Scotty point over here, where everything for this particular technological vein is found, and we get to the Scotty point where applicators like engineers or applied physicists apply this stuff, and the science is done, and the scientists go off and do something else. Okay, at this point, technology, not science, science is done here. Okay, but technology is advancing at a very, very rapid pace. And I should have made this a little bit more asymptotic, which means vertical. Okay, so that is why technology is the important point, because technology is the thing that we're improving with empiricism and science. And again, we start off with empiricism, and here we start using both to transition to a fully scientific understanding, and we use science to find the rest of the missing pieces. Maybe some empiricism is still used here, but then we get to this point, everything is known, and Scotty takes over from there, because you never did see a physicist on the engines of the Enterprise. That's why we're calling it the Scotty point. So let's look at what we claim to know now. Well, this is Newton's law of gravity. Okay, I have a big problem with physicists calling everything laws. This is not a law. This is an empirical model. This only explains if you have how one mass and another mass, the force between them at a given distance. That's all it reflects. It does not explain how one mass couples to the medium, whether you call it the fabric of space-time or the ether, I don't care what you call it. It's a medium nonetheless. How the first mass couples to the medium to generate the gravitational field, and how that field gets to the other mass, and then how that mass then couples to the distortion of the medium. Doesn't explain any of that information. Same here, same here. Now, I know a lot of people are going to say, well, you divide these and whatever, or you multiply these constants over here and you take the square root, you get the speed of light. That does not prove anything. We're going to see that in the next video. Correct answers prove absolutely nothing. That does not prove that these are the properties of free space. And I'm going to show you in the next video that, or you can just go and watch the Ethereal mechanics video series. I'm going to show you that we don't even need these constants in the Ethereal mechanics new electromagnetism version 5. Okay, because ultimately, if all your units of measure are arbitrary, then you do not need an arbitrary constant of relation, because you would just make the units on the left side equivalent, just like F equals ma. There's no arbitrary constant of relation for F equals ma, because they just made the units of force mass times acceleration. Again, if your units of measure are arbitrary, there is no need for an arbitrary constant of relation. So these guys are the telltales that we have empirical models. Okay, and the rule of acquisition that covers this is the 24th. It's the arbitrary tell. If you know what you're doing, nothing should be arbitrary except for units of measure. Okay, arbitrary constant relation indicate an empirical model. That's what these are. This is trial and error. They measured stuff. They fit a mathematical model to mimic it. It doesn't explain any more than the relationship, the force relationship between two masses. It does not explain any underlying mechanism of how these forces are coupled to space, how they get there, and how they couple to the other mass. It does not explain anything. Okay, and the way you would fix this is by saying, okay, this constant needs to be reverse engineered from, or it's got to be derivable from the fundamental underlying models. They have not done that. This G is still an arbitrary constant of relation. They've tried to explain this in terms of the permittivity and permeability, I might have those backwards, of free space, but that is complete nonsense. Okay, so at least they tried with electromagnetism here, but this, they have done nothing. There's no explanation of where G comes from. And I'm going to show you an example of ethereal mechanics where I show you we can derive this from a fundamental model of matter. And that's, again, the fault of general relativity. They have no model of matter, so they can't explain where this comes from. Because if you have a force that's generated from mass, from matter, and couples to matter, then you need to have a model of matter to explain how it couples to the medium. They do not have this. And quantum mechanics can't define it from them. And then people are going to say, well, we have this newer thing called general relativity. Yeah, sorry, same thing. You still have an arbitrary constant of relation in there, making up for what you should be doing, which is real science. These are nothing more than empirical models. These do not even pass the Mendeleev point. That's how primitive we are with these. And because these do not explain any kind of mechanism, nor does quantum mechanics explain a mechanism. Okay, it does not explain a mechanism. And because neither of these have mechanisms, you can't connect them by some underlying mechanism. That's how primitive we are, but we think we're so smart because we have all this technology. Again, we can advance technology without having scientific models. We can do it purely by monkey see, monkey do. And let's look at quantum mechanics. Well, quantum mechanics starts off with discrete states that they call quanta. That's fine. I have no problem with that. If everything is made of particles, and it's logical that all of our energy and all of our other stuff are limited to quanta. I have no problem with that at all. Okay, but the problem is they marry this with a probability distribution, okay, and then they call this whole thing quantum mechanics. Okay, this stuff works, but it's the probability distribution. The problem with it is it's non-causal. Because it's non-causal, you can't assign a mechanism to it, and then you can't connect it, the underlying mechanism, with something else. But as far as a science that's able to, or I won't call it science, this is an empirical method for, producing semiconductors, it's fine. Now, the people who work in semiconductors, no, we do have causal things. We have like potential wells and band gap things. Yeah, but that's all developed from the models I shown you on the previous page, which were all empirical. So this cannot be anything more than empirical. Now, the worst part of this whole thing is that quantum mechanics ran out of things to do, so the physicists got together and they buried Schrodinger's cat in the pet cemetery, and they came back with a cat that's both alive and dead at the same time. And so now we have what I'm going to call zombie mechanics, because now we have all states are entangled, or you consider all states at the same time, rather, and then use probability superposition, okay, which is something I believe physicists made up completely so that they can keep this juggernaut of science going. Now they call this quantum mechanics too, but to me, this is a completely different science. So I'm calling this zombie mechanics. Okay, and where this is covered by the rules of acquisition is the 16th rule of acquisition, which basically says you need a causal relationship between cause and effect. Okay, probability theory is not necessarily causal. When we get to the 16th rule of acquisition video, I'll show you exactly what I mean. People that have studied probability theory realize it's just a correlation. It doesn't explain any cause and effect. It just says, looking over what happened in the past, these things happened this many of the time, this happens this many of the time. Okay, it's not causal. It's just a prediction of what's likely to occur. Okay, and because of that, it's not causal and cannot be part of a theory of everything. Doesn't mean it's not useful. It's definitely useful. Okay, but it can't be part of a theory of everything. But ultimately, though, when a theory of everything is developed, we should be able to derive quantum mechanics from it. Of course, we'll have to throw out all the causality, but we should be able to come up with the same, if not improved, values. And again, the reason why you can't just go from the high level of general relativity and the high level to the lower level to a theory of everything is because, again, I've shown you that these models are incomplete. They're not causal. There's probably, I'm sure there's mistakes in here. I mean, you need dark matter, okay? And they haven't quite figured out a lot of stuff yet, so the models are definitely incomplete. The models here are definitely incomplete because they can't explain a lot of things in the real world yet. Okay, so trying to derive to a lower level from these is problematic. And that's why Mendeleev was successful, because he realized that what he was using was not complete and probably not correct. Okay, and so he started guessing at a lower level pattern, and then using his deck of cards playing solitaire, he would then see if they would fit. And by doing that, he found that from his underlying model, he was able to say, these elements over here have incorrect masses, and there should exist these other masses that we don't see. And that's why the new scientific method requires you to start at an assumption at a lower level and then derive your way back up to the level of the empirical data. And there's a video here about the game of cards that was the birth of the periodic table. Okay, so this is what I did for ethereal mechanics. I found an underlying vortex expression for an underlying field. And this is a pretonic charge, not a Coulomb charge. If you take the time derivative of this, you get the magnetic force model and you get the inertial force model. This is the cause of the force of inertia. This replaces Faraday's law of induction. Now, what I'm going to show you is that this is also the force of gravity, the gravitic force. It's not the field of gravity, it's the force of gravity. And if you go to the intro video of my YouTube site, you'll see a good explanation of what's the difference between the field and the force. Now apply this to a model of matter, which is 2 protons circling at the speed of light. Then you can develop the electric force model. This replaces Coulomb's law. Notice we have no arbitrary constants of relation, but we do have constants that are indicative of the force model here. So this is the rotational velocity, and this is the velocity of the system itself through the medium. And you can see at the speed of light, the electric force goes to 0, which means, well, we'll discuss what that means in a later video. But from this model, because now we know that this model has to consume the medium in order for it to continue this staying in stability and exist, then from that we can develop the gravitational field from the consumption of the medium as these protons have to feed. Also, from this feeding concept, we can also derive the constant g from the model of matter. Again, general relativity does not have a model of matter, therefore they have no understanding of where g comes from. Now, this is the g in terms of natural units. Okay, natural units. Again, no arbitrary constants of relation here. But it put it in terms of how you what it would come out to in legacy units. You divide by km, which is mu over 4 pi. So you essentially just divide this by mu over 4 pi. The blue here indicates that these are legacy units that physicists have been using for God knows how long. And this blue indicates that this is an arbitrary constant relation. It's also in legacy units. So if you put these together, you will find that you get the exact same value of g. The only thing you're going to need that isn't published is the radius of a proton, which is in one of the papers. If you go to my intro video on the website, it'll show you how to get to the paper where that is published. It's for free. You can download it anytime you like. Okay, from this, we now inferring electrogravitic experiment. And from this, we have found an antigravitic effect. Okay, and we've also determined that, hey, under our nose was a vortex version of the magnetic field. This is a spherical model, as opposed to the legacy Biot-Savart, which is a donut-shaped field. It's a cosine field. It's a sine field. Okay, this is spherical. And then we have the latex experiment, which shows that a magnetic field has to be spherical. And that the legacy Biot-Savart model is only showing part of the complete model. And worse, the legacy Biot-Savart model is a vector model. That's not enough information. This is a matrix model. The parentheses here show that this results in a vortex matrix. Okay, let's get on to the next thing. If something were wrong, someone would have said something by now. This is rule of acquisition 27, the smarter monkey fallacy. Let's say you're a scientist and you're working in your crazy laboratory, and you find that one of your cherished models of science has a major flaw in it, that your experiment contradicts this theory, whatever it is. Maxwell's equations, relativity, it doesn't matter what it is. The first thing that's going to go through your physicist brain, because you've been brainwashed, your brain has been shrunk by a STEM education, is that, well, I can't be the first to see this, and then you're going to assume that you did something wrong. And you're going to go through everything to look, and you might even start justifying yourself that you did make a mistake and then drop the whole thing and forget about it. That's what I think most of the people do at this point. Even after you check everything, you will still not publish, because if in fact you are wrong and you publish and the rest of the scientific community finds your error, your credibility is going to be shot to heck. And you're not going to get grants. You're not going to be able to write proposals. Your articles aren't going to be accepted by journals. You're going to lose credibility, and you're going to be basically knocking on the door of engineering departments looking for work in the engineering departments. Okay, even if no error is found, the journals will not publish it, because today journals are worried about their subscribers, and they do not want to piss off their subscribers by insulting them. And not only that, if you are correct and your theory does disprove what all these other physicists are working on, now you've just invalidated all of their fundraising, all of their their articles. You've invalidated all of their grants and funding, because now the things that they said to the grant person giving the grant is, well, now you're not going to be able to do anything because you just disproved the entire foundation of your existence. Why should we give you money? Okay, so you're not only going to be working yourself out of a job, you're going to be working all of your colleagues out of a job. So you're probably just going to say, it's not worth it. I'm not going to be the guy. I'm going to let the smarter monkey deal with it. That mystical person that's supposedly in charge of science. Let him deal with it. Okay, I'm certainly not the smartest monkey out there. Okay, and the thing that's the cherry on the top is that there's no money in it. There are no grants for proving existing theories wrong. There are no awards for proving something wrong. I've even thought about starting my own award called the No Bull Prize. I thought it'd be funny, but unfortunately, it's a waste of time because no one would take it seriously. This will be covered in more detail in the 27th rule of acquisition, which is smarter monkey fallacy. That might be the third or fourth video out. Okay, but there's another part of the smarter monkey fallacy. Is there an implied statute of limitations? In other words, by now. Somebody would have said something by now. Well, I'm going to show you that's another fallacy, because in certain cases, it may have taken 2,000 or 3,000 years before counterexamples may have been encountered. And let me give you the case of our Archimedes principle. It's been around for 2,000 years, and it basically says that the buoyant force holding up a ship is equivalent to the weight of the water displaced. And in circa 1900, which is about 2,000 years after Archimedes published this, we have a ship. This is based on a real story that was going at normal speed into the bay for picking up passengers, unloading cargo, whatever. And every time it's come in, it's always cleared these reefs and rocks at the entrance to the bay. Then one day, trying to outrun a very, very bad storm, it ran into the bay at full speed, and unfortunately, a phenomenon that no one had known about, because it's not anticipated in Archimedes' principle, called hogging occurred, where the ship sank down lower in the water, because going at high speed actually lowers the pressure. And again, our pressure was not a concept that Archimedes even knew. Pressure was something that came up, I think, 1800s. But they didn't know that it would affect ships at that time. It's called Bernoulli's principle. And because of that, the ship squatted down in the water. It hit the rocks. You get loss of life, loss of property. And then it took a while for scientists to realize what happened. Okay, so it took over 2,000 years after Archimedes' principle for humanity's footprint to expand in terms of ship propulsion before the phenomenon known as squatting presented itself as a counterexample. So it took 2,000 years for us to advance our technology, 2,000 years of stagnation leading to loss of life. Now, what would it be if we had a tool back in Archimedes' day, that would have said to his principle, well, this principle is wrong. It can't be correct because it violates these rules of acquisition. Maybe they would start looking for another answer. Maybe they would have discovered pressure in Bernoulli's principle thousands of years ago and determined the proper buoyancy, and then we would not have had this loss of life and property 2,000 years later that led to the advancement of science. Okay, so let's go back and show you how the rules of acquisition would have applied in Archimedes' day. So Archimedes' principle says, again, that the buoyant force acting on a ship's hull is equivalent to the weight of the water displaced. The problem with Archimedes' principle is it doesn't tell you where the force is applied. Is it applied at the bottom of the ship? Is it applied at the top? Now, granted, a lot of people are saying, well, we know that from pressure and Bernoulli. That stuff wasn't back in Archimedes' day. They didn't have any understanding of pressure. Okay, so what would have happened is they would have looked at this model and said, hey, because you're not telling exactly where the pressure is applied and it's more like a distribution of pressure, force on the hull, because they're not explaining that, then this violates locality, which is a spatial connection between action and reaction. Action-reaction cannot occur temporally or non-locally. Although it's allowed for simplified models, like we can still use Archimedes' principle, And now we just have to caution ourselves that it doesn't apply when ships are going at high speed. Okay, so now we have a limitation on what we thought was an irrefutable model of science. Okay, and this is how we could cut short circuit by applying these rules of acquisition to everything we know now, and we can cut out these models that are not correct. Okay, and again, we wouldn't have had to wait 2,000 years for a calendar example, loss of life, before we can have scientific progress. And again, I am really not the first to realize this, because Emer Lakatos said we should not think that a theory is ultimately true. True, a word we need to define. We'll define it in the next video. They use the word final and true, and there's a lot of confusion between what the word true means in terms of science. Only that no counterexample has been found yet. Again, as I've shown you, when we develop scientific models, we tend to develop them with all the known stuff in our existing footprint. And what we don't do is when our footprint expands, we don't recheck the models to see if the new information in our new footprint doesn't have a counterexample. That's something we need to start doing, is whenever the footprint expands, that's one of the imperatives we need to do, is recheck all of our models. Because there may be new information that we know now that might contradict what we think is an irrefutable model. Okay, I'm going to make one more final point. Again, the objective of science now, this new definition, is to find the underlying models at which some scientific theory or observation works. But we have a problem here, is because even though now we have an underlying mechanism that allows us to know what's going on underneath the rest of the puzzle, the problem is this may just be another puzzle, and underneath that is another mechanism. It's no guarantee how deep the rabbit hole goes. So just because we have found this mechanism doesn't mean we're done. And let me give you an example going back to fire. Okay, remember, in fire, we say, what is fire? It's a chemical reaction. Okay, what causes a chemical reaction? Here we go. This is the Google AI. When molecules of different substances collide enough energy to break their existing bonds. Okay, so what causes atomic bonds and chemical reaction? Atomic bonds are caused by the electrostatic attraction, blah, 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 which lead to valence. What causes the behavior of the valence shells? It goes down and down and down. Eventually, you should be able to get down to the point where it is the protons and neutrons in the nucleus of the atom that govern the valence bonds and what their behavior, their number is. And then you go, well, what governs the protons? And then you're getting down into quarks. And what are quarks made of? All the way down to the bottom. So just because we know that fire is a chemical reaction does not mean we're done. We still don't have all of the knowledge, complete knowledge of what fire is. So one day, though, okay, we're going to sit there and say, okay, well, quarks are made from protons, and protons also make electrons, and then protons and neutrons are made from quarks, and quarks, neutrons, and electrons make atoms. Atoms form together to form molecules, and it's the action of atoms and molecules that explain fire. So we would need to go all the way down to the bottom level of however many levels the puzzle is. Work from the complete bottom and work every theory, every model, all the way back to a description that mimics fire. And then and only then can we have confidence, not perfect confidence, because we may have come up with a completely false method that gives us the correct answers. Again, we need to be skeptical all the time and be open-minded to other things that say, this might be wrong, or that might be wrong, or this might be wrong. In fact, in ethereal mechanics right now, it looks like protons are a spinning system made of something smaller. Right now, the preliminary word for that are pixons. But that's for ethereal mechanics. But this is the idea. You work from the lower echelons to the top to see if your observables can be created by the underlying models all the way down to the bottom of the rabbit hole. Okay, so let's have a recap. We demonstrated that the present scientific method, which waits for falsification for thousands of years, is one of the causes of the stagnation of science. We need to find other techniques like the rules of acquisition, which can detect flaws in models and therefore get rid of them so that we can go on to the next one, so then we can start developing suitable models for a theory of everything. And I've shown you that general relativity and quantum mechanics fail the rules of acquisition and are empirical models at best. Again, they haven't even crossed the Mendeleev point yet. Okay, and I showed you an example of ethereal mechanics, which shows a coherent underlying mechanism which is compliant with the rules of acquisition and comprehensively unifies gravity, electricity, magnetism, and inertia with a model of matter. And we're demonstrating a new language for what we're going to call technological development to replace the confused and abused scientific method. Okay, this is the end of the introduction video. I'm going to get into some administrative stuff. The next video will explore the rules of acquisition. The next videos will explore the rules of acquisition, not necessarily in singular or in numerical order. For example, the next video covers the following group of related rules of acquisition: 1, 5, 39, and 40. Okay, in this next video, we're also going to complete the definitions that support this series, as well as release the flowcharts for the new methods. After that, the following rules of acquisition will be released in no particular order. Furthermore, when cosmology release begins, the rules of acquisition will be paused because these rules of acquisition are fill-in until the major papers are actually produced. Then we'll get back to completing these. Okay, but again, as we go through the rules of acquisition, we are going to have a spreadsheet that's going to show which rules of acquisition a particular scientific model, theory, law violate, to show you that these things are substandard and cannot be part of a theory of everything. Now, I've only shown a little bit of what I'm going to actually put in there. So if you have other models you would like to suggest before we start, please put the comments what other models you'd like to be applied to this litmus test. This is our Patreon site. This is the best way to support ethereal mechanics. This is the repository. It's located at distinti.com. The intro video of our YouTube site, you can get there by etherealmechanics.com, or if you go search ethereal mechanics on YouTube, look for the girl in the ring of fire. The intro video here will explain how to get around the repository to find all the papers and how to get around this site, because all of our different papers are in their own playlist. Okay, it also gave you an overview of ethereal mechanics, where it stands right now. This is our blog site. Big shout out to Sebastian. Again, if I can get enough Patreon members that I can do this full time, I'll have time to spend here. Right now, every moment is spent between my job and this. I have not taken a real vacation in 20 years. I don't think I have. No, have not. Again, thank you. No more voodoo physics.